Hello algebra students. In this lesson we're going to be finding the sums of infinite geometric series. As you think about finding the sum of a series, if I put up the word infinite in front, you might think that there would not actually be a sum. I can always just add another term if it goes on to infinity. What we're going to find out in this lesson is that sometimes a geometric series that's infinite can have a particular sum. To consider that, I want you to take a look at the series listed right here. 2 plus 2/3 plus 2/9 plus 2/27 plus 2/81 plus ... An infinite series. Geometric in nature because to go from term to term, I'm multiplying by 1/3. That's my common ratio. Now what we're going to do is we're going to find some partial sums for this particular series. Now a partial sum is when I'm taking just a couple of terms from that series. So what I'm going to do first is I'm going to find the partial sum of just the first term. I'm going to jot these down over here. So the sum of one term in this series would be 2, okay, because 2 plus nothing is 2. The sum of the first two terms would be what I get when I take 2 plus 2/3. Okay? Partial sum of the first three terms is going to be 2 plus 2/3 plus 2/9. And so on. The sum of four terms would be 2 plus 2/3 plus 2/9 plus 2/27. Then I've already added the fifth term to that, 2 plus 2/3 plus 2/9 plus 2/27 plus 2/81. Now what I want to do is I actually want to have a sum for these particular items. So I've got the terms all written out. Now to show you what the sums would be, well, the sum of the first term is 2. Okay. When I do the next one, 2 plus 2/3 is going to be 8/3, or as a decimal, you're looking at about 2.6. Actually, it's 2.6 repeated. If I then add 2/9 to that, suddenly I'm looking at an expression that's equal to, if you can check all this stuff out if you don't trust me, but it's going to be 26/9. Okay, adding that up as a decimal, 26/9, you're looking at that turning into 2.8 repeated. When I add 2/27 to that particular sum, now I'm looking at having 80/27, okay, which is approximately as a decimal 2.96. Okay, so when I add 2/81 now, some teeny tiny fraction to the sum that I already had, now I'm looking at a fraction that is 242/81. As a decimal, you're looking at 2.99 if I were to round it to the nearest hundredth. You'll kind of notice that I went 2.6, a little bit of a jump, 2.8, not so much of a jump, 2.96, smaller and smaller. Now if you were to graph these points on a coordinate plane, here's what I got. When I plugged in 1, the sum of the first term was 2. When I plugged in 2, took two terms for that series, I ended up with 2.6-ish. 3 terms added up to 2.8-ish. 4 terms, you're looking at 2.96. 5 terms, looking at 2.99. Okay? What's happening is these sums are getting closer and closer to a limiting value. In this case, the limiting value is 3. So it's not as if we can say it is exactly 3, but it's getting closer and closer to it. Now, if I were to keep adding terms, the next term, well, that'd be 2/243, a really tiny fraction. And every term from there is going to be a smaller and smaller fraction. I keep adding smaller and smaller fractions, smaller and smaller values to this value, 2.99. I'm just going to keep getting closer and closer and closer to 3. Hopefully that makes some sense. Algebraically, here's what that process would look like. If I wanted to find the sum of n terms of a geometric series, the formula is this. You take the first term times 1 minus the common ratio raised to the nth power divided by 1 minus r. Now in this case, if I want to find the sum of this infinite geometric series, things I know. I know that the first term is 2. I know that my common ratio is 1/3, so I take 1/3 to the nth power divided by 1 minus 1/3. Parentheses around that. I want you to think of this. If this is an infinite geometric series, the number of terms goes on forever and ever. So n approaches infinity. Here's what I want you to think about. As n approaches infinity, you plug in a really, really big number for this expression right here. Well, 1/3 raised to the 10 millionth power, let's say, is going to be 1 to the 10 millionth, which is 1, over over 3 to the 10 millionth, which is some gigantic number. So I've got 1, little tiny 1, over a huge number. Well, 1 over a huge number is going to be an awfully small fraction. It's basically 0. So this expression right here, as n approaches infinity, this expression is going to approach 0. This expression is basically 0. Now if I replace that with a 0, check out what happens. What's 1 minus 0? 0. So if I were to rearrange this expression a little bit, let's look at the 2. And now I'm multiplying by 1 minus 0, which is 1, over 1 minus 1/3. Well, 1 minus 1/3 is going to be 2/3. Okay? So I have 2 times 1 over 2/3. You know what we say about dividing by fraction? Instead of dividing by fraction, we should multiply by a reciprocal. So let's do this. Let's multiply everything by 3/2 instead. So instead of dividing by 2/3, let's multiply by 3/2. So now I got 2 times 1 times 3/2. Well, 2 times 1 times 3/2, cancel a couple of 2's, that's going to equal 3. 3 is the value that we figured that we were approaching as we added up the couple of terms in our partial sums. Now, in the next video, we're going to look at the particular formula that we can derive from the work that we did right here, turning this term into a 0.